Hello everyone. In this session, I'll discuss about surface tension. Here I have drawn a sketch wherein some of the sand grains or food grains put on a cloth, and then this is made into a shape like this. Ends of the cloths are joined together and all those grains are held together. So naturally obtained shape is something like a sphere only, and the cloth is under tension and all the grains are held together inside. The surface which is holding the grains together is under tension. So everyone knows this particular phenomenon. We don't try to give a shape, but naturally acquired shape by grains, if they are perfectly spherical and without much of difficulty, obviously they form a perfect spherical shape. So a cloth which is holding free grains, when it is held in this particular shape, it will be spherical, and the cloth which is on the surface of these grains is under tension. So the surface material is under tension, so that is why the name is surface tension. Now in this case obviously the cloth is under tension, but in case of any fluid, it will be in the form of, let us say, a droplet, right? Or any surface when it produces. Here very nicely depicted, inside molecule, if you take, all the molecules are equally attracted because of the cohesion towards each other. So a molecule which is inside is under equilibrium, right? Every molecule, if you take, it will be equally attracted, right? So there is nothing like tension or compression, it is equally balanced. But if you take a molecule which is on the surface, here it is exaggerated. Now you can see that it is pulled inside as well as it is pulled sidewards on the surface. More interesting figure is over here. So if you take a molecule here, it is attracted and pulled by all other molecules, which is in balance. But if you take a molecule on the surface, it is attracted towards this way and this way. Another molecule on the surface will be having the same type of attraction. So if you just observe all the molecules on the surface, they are holding hand and then protecting the molecules which are inside. So like that it happens. So these molecules which are present on the surface act like a cloth to hold the grains inside. So obviously the molecules which are holding all other molecules inside will be under tension. So that particular uh, property of liquids to contain other molecules inside them with one layer of molecules on the surface which is under tension. So this particular force is known as surface tension force. So due to surface tension, water droplets and soap bubbles are in spherical shape. Hello, we'll continue the discussion of surface tension here. By definition, surface tension, it is the tensile force that is developed on the surface film per unit length. This is developed due to molecules developed to keep the molecules at the surface in equilibrium. we'll discuss this in equilibrium, denoted by, the surface tension is denoted by sigma. The units of measurement will be Newton per meter length, because it is defined force per unit length. That's why units will be Newton per meter length. Obviously, the dimension becomes m L raised to 0 T raised to minus 2. Now, if you look at this free body diagram of the molecule at the free surface, if at all there is any object which is sitting or floating on the object, it will be slightly curved like that. So this is the molecule of water that we are trying to analyze, and these are molecules which are present on the sides, and there is a cohesion between these two, and because of that the force acting on this droplet will be in that direction, slightly inclined. Will have one component upwards, one component sidewards, and they are shown here. Similarly, this attractive force is resolved into two components, this way and this way. Okay. Now these two components which are going upwards are balanced by the force which is uh, being pulled in due to cohesion, and other molecules which are present inside are trying to pull this down, and they are balanced by this upward force. So these two are components help to keep the molecule in equilibrium, and these components which are there here are having a tensile force because of the existence of other molecules on the side. So that tensile force which is on the surface is known as surface tension. Now similarly, if I take a free body diagram of the molecule on the surface of a drop or bubble, if you look at this way, this is a molecule under consideration. There will be reaction, and that reaction will be having two components, vertical and horizontal, and there will be a cohesive pull inside because of existence of other molecules also, right? And there will be a force of attraction because of other molecules also. So these cohesive forces will have two components. One contributes for surface tension, the inward pull components to keep the molecule in equilibrium, because there is a reactive force. The reactive force will be having a force like that, which is trying to push the molecule outwards, but it is balanced because of component of the force, cohesive force, which is there on the adjacent side, right? So overall, what I want to say is the pull and then push are balanced, but sideward, whatever force is there on the surface, sideward on the surface, whether it is on the surface of drop or bubble or on the free surface, this tangential force or the force along the surface is surface tension, or force due to surface tension. Okay, here in this we'll try to study relation between pressure, surface tension and diameter of the drop. So whenever drop is formed, it will be having some pressure, additional pressure more than the atmospheric pressure. That extra pressure we will represent it as delta P, because outside there is an atmospheric pressure, inside there will be pressure slightly larger, and that pressure, difference of pressure, will be represented as delta P. Now consider a drop of water, diameter D, inside pressure delta P more than the external pressure. Consider equilibrium of 1/2 of the hemisphere. Okay, when you cut this into two halves, obviously the diameter remains D fine, and inside all this surface, the surface area of a circle pi d squared by 4 is applied by a force of delta P. So there is a resultant push P will be acting, which will be equal to pi d squared by 4 multiplied by delta P. So the total push, that will be this much. But the two halves are held together because of the force that is acting on the periphery because of the surface tension force. So surface tension all along the periphery, it will be acting. What is the length of periphery? It will be nothing but pi d, because d is the diameter, and force per unit length is sigma. So the total force which is acting along the periphery will be pi d into sigma. And when the drop is existing, these two forces should be balanced. So equating the two for equilibrium, this pi d squared by 4 into delta P should be equal to pi d into sigma. From this, we can see that it is delta P is equal to 4 sigma divided by d, indicating that inside extra pressure will be equal to 4 times the surface tension divided by d. One can analyze here the diameter of the bubble. If it is less, the pressure inside will be more, and then if the diameter becomes larger, then the pressure inside becomes lesser. So to say, if you have got a smaller bubbles, they are not easy to disturb, but if you have got a bigger bubbles, uh, not bubbles, drops, obviously it will be easy to break into smaller droplets. Okay, we'll go to the next slide. Here we'll be talking about bubbles. So here there is a bubble. Whenever there is a bubble, there is air inside. Unlike in droplet, where water molecules will be present inside. But here what happens is the water molecules are present only in the periphery. Outside as well as inside there will be air. But in case of bubbles also, the pressure will be slightly larger inside than the atmospheric pressure outside. Moreover, whatever thin film which will be making a bubble will be having inner surface as well as outer surface, because there is a thickness for the bubble film. Though it is quite thin, it will be having some thickness, and then inside there will be a surface, outside there will be a surface. The analysis will be like this force which will be acting on this circular surface because of extra pressure inside the air that is present inside the bubble will be balanced by the surface tension which is acting along the periphery, and that periphery will be inside periphery as well as outside periphery. There will be two peripheries with the same diameter d almost, because this thickness of the film is quite negligible compared to the size of the drop. We'll go into the details. Analysis of soap bubble. Now I have shown a soap bubble of diameter d. Thickness of the film is exaggerated slightly so that we can understand it is quite negligible actually compared to the diameter d. So there is a surface tension force which will be acting at a rate of sigma Newton per meter length. So the total force will be 2 times pi d. There is inner surface, outer periphery, that is 2 times pi d multiplied by sigma. So that is the force which will be holding on to the other half. Now what is the force which will be trying to push it out? That is P, which is acting on pi d squared by 4 area with delta P as the extra pressure. Now for equilibrium, now these two forces should be equal. So I put it as 2 pi d sigma from this equal to, from this, pi d squared by 4 into delta P. From this it becomes delta P is equal to 8 sigma by D. So here also more the diameter, lesser the pressure, right? Lesser the diameter, more the pressure required, or pressure will be there inside the droplets. That's why generally bubbles of larger size are easy to break, and if the bubbles are of smaller size, the durability or the retainment of the bubbles will be quite more. That is the reason why that can happen. Because of this expression we can explain. Now if you take a jet of water, and then if you consider small length L, here I have shown L, and then cut the jet into two halves. Generally the jet will be having a circular cross section, and it can be considered as a cylinder for a smaller length. So I have shown here a length L of the jet, and then only half of the jet is shown longitudinally along the length. There is a cut made, and lower half is shown over here. The diameter of the jet is D, the length is L. So the surface over here, on the surface, it is a rectangle with the width D and length L. Now surface tension force will be acting along this length as well as along this length. There are two lengths which will be holding the surface tension force. Now that will be balanced by a pressure force which will be acting on this area of D into L. Now what is the total force which will be acting on the surface? P will be equal to the difference of pressure, means the pressure difference outside and inside, delta P, multiplied by D into L. So this is the total surface tension force. Total surface tension force will be along these two lengths. So L plus L multiplied by sigma. Sigma is nothing but surface tension force per meter length. So total it becomes 2L sigma. Now for equilibrium, these two should be once again be equated, equating the two. For equilibrium, delta P into D into L will be equal to 2L into sigma. L cancels off. We get delta P is equal to 2 sigma divided by D. So the pressure inside the jet will be equal to 2 sigma divided by D, 2 times the surface tension divided by D. Even in this expression also we can infer in the same manner that lesser the diameter, more the pressure, right? More the diameter, lesser the pressure. Because of that, the jets having more diameter are volatile, or they may get disturbed at any time. But if you got a jet of lower or lesser diameter, they are quite stable. Okay, thank you. We'll stop here.